I teach math at Dickinson College. I'm also the editor for Math Horizons, and I want to talk about a cool theorem that I learned about. Doesn't really have anything to do with most of the rest of what I do, but I got intrigued by this and started working on it more and more, and have some interesting things to say about this theorem. As many of you probably know, there was this interesting tradition in Japan. This was during the period when they were sort of isolated from the rest of the world. They had this tradition of bringing mathematics into their temples and shrines in the form of these beautiful wooden tablets that they would hang. There are these lovely geometric problems. And the theorem that I want to talk about is one of these problems. It's called the Japanese theorem. That seems to be the name that it has, but that could be applied to many. Unfortunately, the tablet that contains this theorem is lost, but we have a written record of what was on it. So I'm embarrassed to do this in front of this artistic audience here, but I made my guess of what this might have looked like. And this is the description that has come down to us. It says, draw 6 lines in the circle and make 4 circles inscribed in 3 of the lines. If the diameter of the southern, eastern, and western circle is 1 sun, 2 suns, and 3 suns respectively, how long is the diameter of the northern circle? So essentially in this picture here, that lowest red circle has diameter 1. The blue ones have diameters 2 and 3. We have this situation where there's this quadrilateral with the 2 diagonals, and these are inscribed circles. And the question is, how big is the large red circle? So that is the problem. And again, we believe this was from around 1800 when this was posed. And so this is the way the answer was written, is 4 suns. And the description of the solution is to add the diameter of the western circle to that of the eastern one and subtract that of the southern one from it, and you will get that of the northern end. So in other words, 2 plus 3 minus 1 gives you 4. But there's nothing special about 1, 2, 3, and 4. I mean, there is something special about 1, 2, 3, and 4, but not in this theorem. There is this more general result that if you take a quadrilateral inscribed in a circle, convex like this, there's 2 possible diagonals that you can draw. You can inscribe circles in each one of them, and it turns out that the sum of the radii in the 2 cases are the same. So this was the original statement of the problem. As I move these vertices around, you can see that the sums of the radii are the same. So that is the way the problem was stated. A little later, 100 years later or so, it was observed that you could create this fan-like pattern for an inscribed polygon, and that it doesn't matter which vertex you choose to create this fan pattern, the sums of the radii are the same. And in fact, if you think about it, there's nothing special about this fan-shaped pattern. It was also observed that if you take one of these cyclic polygons and triangulate it with diagonals, then the sums of the radii of these circles are the same in those cases as well. This example, if we show multiple circles here, we're going to get the same sum in each case. OK. And so we had some questions about this. You could ask some questions about this. For example, how large could you possibly get for one of these things? And the result is that the largest possible radial sum that you can get is via a regular n-gon. And then the question is, OK, what if you increase n? How large can this radial sum be? And it turns out that it approaches the diameter of the circle. And so I have this nice visualization which shows why that's true. I have this set up in a very specific way, and the circle's set up in a specific way, and the radii laid out in a specific way. And you can see that this is pretty close to the diameter of the circle. OK, and so let's try this again. So drag it over. Now I know the trick. And so here's an example where I increase the number of sides. And you can see that as we do that, it gets closer and closer to the radius of the diameter of the circle. OK. And finally, let's see here. Finally, in that original applet, or the second applet that I showed you, there's this temptation to drag one vertex behind the next one to get something that's non-convex. And so the question is, can you say anything about that? You could still make meaning of triangulating with not, quote, non-intersecting diagonals, whatever that means in this case. But now suddenly you get circles which, if you do the dragging, they kind of flip around backwards. And so the question is, can we make use of that? And it turns out the answer is yes, there is a Japanese theorem for this. It's just when it flips around backwards, you subtract the radius instead of adding the radius. And so let's see here, I believe it's this one. And so here, if we pull one of these guys around behind, they introduce negative signs here and a negative sign here, but you still get the same radial sum. So that's sort of interesting. And so if you would like to read more about this, this was just posted online recently to the MA's LOSI, which is their online journal. And there's a bunch more applets available there that you can play with. And also, Princeton University Press had a book out not too long ago about these Japanese temple problems. So you may want to check that out. So I think I'll end there. Thank you.